kind of like trying to turn a Phillips head screwdriver with a straight screwdriver. It's just not the right tool for the job. Understanding the model coefficients, let's say that we have y hat, again the predicted y, equals 30.3 plus 1.36x. Our intercept in this case is 30.3. The interpretation is, and I'll tell you right now, I'm very picky about this, your interpretation on a test or whatever needs to be exactly what I'm telling you here. The interpretation is when x is equal to 0, the predicted y value is 30.3. So whatever your intercept is, let's say it's negative 11. When x is equal to 0, the predicted y value is negative 11. Let's say this is 14.7. When x is equal to 0, the predicted y value is 14.7. It should make a little bit of sense, because if we put x equals 0 in our model, again, just put 0 in for x, you can see that 1.36 times 0 is 0, and we get our y hat, our predicted y, just the number that is in the spot of the intercept. Slope's a little bit more challenging, but not much. The slope here is 1.36, and our interpretation, again, needs to be exact. As the value for x increases 1 unit, the predicted y increases 1.36 units. If I had a negative 5 here, my interpretation would be as the value for x increases 1 unit, the predicted y decreases 5 units. If I have plus 42 here, as the x value increases 1 unit, the predicted y increases 42 units. So the words are always the same. What changes is just the tail end of the interpretation. Now this should kind of make sense, because let's just put x equal 1, x equal 2, and x equal 3 into our model. So 1, 2, and 3 go in for x, and I create different predicted values. Notice that from 31.66 to 33.02 is 1.36 difference. Notice from 33.02 up to 34.38, the difference is 1.36. So as I increase 1 unit, the predicted y increases the amount of the slope. Now, we can use our model to make predictions. And the first thing we need to decide within a problem is which variable is x and which is y. Regardless, y is always the variable that we're going to predict. Now, sometimes this distinction can be a little challenging, but if a variable comes naturally first, chronologically first, then it must be the x. We can't predict something from something that occurred later. It doesn't even make logical sense. So if I have an example of like a blood pressure when admitted to the ER, and I'm examining the relationship between that and a blood pressure when discharged from the ER, well, clearly the x has to be the admitted BP and the y has to be the discharged BP, because the admitted would naturally and chronologically come first. But for white blood count and red blood count, I don't think, maybe medically there is a reason, but neither one comes naturally first. So, sorry, I had to take a cup of coffee, drink of coffee. I'm still fighting COVID. Now, this has been a strange experience. I had COVID in July of 2022, and I'm creating these videos in December of 2023. And the symptoms are about the same. I don't think the severity of the symptoms are any different, but it's just lasting longer. I think in 2022, I probably had symptoms for about 3 to 4 days. Lost my smell and just some stuff. I'm not going to go into that. But this time, same thing. Lost smell for like 4 days. But it's just going on. I'm like in my 8th day now, and I'm starting to feel better, but still just not kicking it as quickly as I thought. So I still have the Barry White voice. Anyway. So let's just say that we want to predict red blood count from white blood count. So my X is white blood count, my Y is red blood count. Super, super easy to put into R. Run a model, and this hashtag, I'm just communicating to you that the LM command is always LM. We put our Y first, our tilde second, and our X third. When we have one predictor. And we're going to go through so many examples of this. If it doesn't make sense, we'll dive into a bunch of examples. And the output is a little strange. I'll go through all this with a fine-tooth comb in a later video, but for right now, I want you to know that this 1.44 right beside of intercept, that's our intercept. And whatever is under estimate beside of the other line, this is our slope. All right, so for our model, we would conclude that red blood count can be predicted by taking 1.44, that value right here, plus 0.42, this value right here, times the white blood count. Notice I just replaced X with white blood count because that's what X is in this problem. The way I've set it up, I've replaced Y with red blood count because that's the way we set it up. We are predicting red from white. Now, the intercept is 1.44. What's the interpretation? The predicted red blood count is 1.44 when white blood count equals 0, or when white blood count equals 0, the predicted red blood count is 1.44. The slope, as white blood count, our X, increases 1 unit. The predicted red blood count increases by 0.42 units. To use this model to make a predicted red blood count, when we have, for example, a white blood count equal 9.3, we can say that their predicted blood count can be found by just putting 9.3 into our model, and we would predict that person's blood count based on their white blood count being 9.3 to be 5.35. Now, do you think we always get it right? No, we don't always get it right. We have error in these models. And mathematically, we seek to minimize these errors. But let stat geeks like me worry about stuff like that. You need to be able to use regression in your field. You need surface level knowledge of this technique. So, can we predict a red blood count when white blood count is equal to 12? Well, we can't. Let me explain why. This would require what I call extrapolation. Notice that our lowest blood count was 4.8. Our highest blood count was 10.9. So predicting a Y value outside the range of the X values we have in our sample requires extrapolation. Our model was just not built to predict red blood counts for white blood counts this large. It'd be kind of like collecting data from kindergartners and then using that model in a nursing home to make predictions. It just wouldn't make sense because that's not what the model was built for. And our model was not built for predicting red blood counts outside the range of white blood counts from 4.8 to 10.9.